All right, last session of the day. We have a great panel lined up for you on surface finish and post-processing. We're going to pull those ladies up to the stage. I can go ahead and tell you who these ladies are. We have Stephanie Barberree from post-processing. From REM Surface Engineering, Alena Folger from DyeMansion, and Alex Kingsbury from RMIT University. And I will leave the more detailed introductions to the panel as we get everybody up here.
We need Alex also there.
Sometimes it just takes a minute to pull people up. And once you're on stage, you'll need to turn on your camera and mic. And I forgot to introduce our moderator, Krish. She is with Henkel. And she has been doing a lot of prep for this panel, so I'm very excited to hear. And so, let's see. Alex, I think you may need to put yourself on stage because you have host privileges.
Okay, Dana, sorry about that.
Who else are we missing? We're missing Stephanie. Oh, there's Alex. All right, one more.
So it looks like Stephanie's on the stage already, Amy, okay. But just her
all right, well, Stephanie,
cam is not on.
Yeah. All right, so Stephanie, if you can turn on your camera and mic. Let me get you up here. So why don't you ladies, I'll leave the stage. I'll let you guys start introducing yourself and we'll let Stephanie bring herself up.
Okay. I'm sure Stephanie will be joining us soon. Shall we give it a minute and then start?
So if I go to Stephanie, it just says my only option for her is to remove her from the stage. So she would be already on the stage and may just have to turn her cam on.
Okay. So how about, Chris, you want to start with your introductions, just keep the panel going and
yeah, okay.
We'll shoot with Stephanie. Thanks.
Yeah, let's have Stephanie join in and then we do the rounds. Okay, so hello everyone, and hope you're having a very good time at the Thai PE conference day 1 so far. I'm Krish. I'm an aerospace engineer turned business professional. I manage market customer activation topics for Henkel Adhesives incubator businesses, so which also includes 3D printing. So we are a brand of Loctite, you might know, and we focus primarily on photopolymer materials for DLP SLA technologies. And also post-processing technologies like coating, infiltration, cleaning, bonding solutions, and so on. But that's about me, and I will be the moderator of this session. And today we are going to talk a bit about surface finish and other post-processing technologies. And we have our wonderful panelists here who have also experience in the similar fields. So let's go around for a quick round of intro and also understand what they would like to share within the session. Alena, would you like to go first?
Oops.
Pleasure, Krish. So, hello everyone. I'm Alena. I'm a chemist by training, and after my PhD, I had the chance to start my 3D printing career at DyeMansion. So here as a head of R&D, I'm responsible for the development of new finishing processes for 3D printed plastic parts. And now I'm really looking forward to showing our audience how post-processing can unlock the full potential of AM.
Lovely. Exactly what we want to explore in this session. Alex, maybe you go next.
Yeah, sure. Hi. How's it going? Thank you so much for having me on the panel. My name's Alex. I'm an industry fellow in additive manufacturing for RMIT University. So industry fellow is a slightly unique position within a university, but basically it means I'm sort of the bridge between academia and industry. And I've been in additive for quite a number of years now, and that's really always been my role in one way or another. Has been trying to bring research into industry, really looking at translational research. Where I started though as an engineer was in doing a lot of commercialization studies, and so as part of that we do cost models, and the cost models when additive was starting to come out and come together, and we were starting to look at proper industrial applications for additive, I was doing the costing on the post-processing, and it was enormous. And so I very, very quickly realized in my additive journey how important post-processing was, and also, probably more importantly, how there's so many different trade-offs that you can have with post-processing and surface finish that go to cost and to performance. So excited to join the panel, and I'm really hoping we get Stephanie up soon too. We're obviously having a few technical issues.
Thank you, Alex. Jeniree. Stephanie is here.
Sorry about that.
But glad to have you here.
Yeah, me too.
Jeniree, why don't you go next, and then we go around to Stephanie.
Sure. Thank you for having me in the panel, and I hope everybody's enjoying the conference so far. My name is Jeniree Flores. I go by Jenny if that's easier for everybody to pronounce. I'm also a PhD in chemistry, and my career, actually my graduate career started in polymer chemistry, but now I am a senior research scientist and technical marketing manager at REM Surface Engineering, and we really specialize in post-processing or surface finishing solutions for metal additive manufacturing. The majority of my work at REM has been based on aluminum alloys, though, really developing the surface finishing solutions for aluminum-based additive manufacturing parts. And really what I would like to show today is how surface finishing can really help the manufacturing industry widely adopt additive manufacturing, because like Alex said, it has huge impacts on performance and cost. So really, as the better we understand it, the more we can get to full adoption of the technology.
Thank you, Jenny. Stephanie, would you like to introduce yourself, please?
Sure, I'm very happy to be here. I'm Stephanie Barberree. I'm the West Coast Business Development Manager for Post-Process Technologies. And it's my responsibility to educate new and existing customers about our fully automated line of post-processing solutions. We specialize in resin removal, support removal, and obviously surface finish as well. I've been in the additive industry for many years, so very happy to be here and very happy I got my camera working today. Thanks.
Okay, perfect. Thanks for your introduction, everyone. So let's get this session started. Now, we all know every application has its own needs. And as a community, what we want to do is support each other through the journey towards additive manufacturing and exchange learning so that we all can benefit from each other. And with the industry experts in surface finish and post-processing technologies today, today's session, we will cover what are the different challenges and what's the status quo and what's the outlook of such technologies, and understand their impact in the additive manufacturing space to get reliable, high quality finished parts. Let's start with why. So why do you think that post-processing technologies or surface finish, to be a little bit more precise, is important. So I leave this open to the panel to pitch in.
So, well, maybe for me, if I start, post-processing is crucial to really get 3D printed products becoming part of everyday life, because only post-processing enables so many new applications, and it's also essential to achieve end-use parts. So, for example, if you start with a raw sole like this, it looks okay, but it's not a real part. But if you use post-processing, you can end up with a really nice shoe in the end, like this one. So I think this is the great opportunity we have with post-processing.
I can go next. Yeah, sure. I think with automated post-processing equipment being introduced in the marketplace, we're seeing a displacement of more traditional manufacturing methods. And as we all know, surface finish is crucial to additive parts. It just creates a smoother, more uniform look.
Yeah, thank you, Alena and Stephanie. And I think it's a great point that we see more and more applications come to the light every day. And surface finish is not just constrained to aesthetics, but also expands to functional needs. Maybe like something like UV resistance or environmental resistance. If we start thinking about a more simplified image of a 3D printed sprinkler in your lawn, the first thing you might need is a material compatible for outdoor weather conditions. But maybe additionally, it also needs the waterproof coating. And I think post-process technologies has immense potential to bring additive manufacturing one step closer to the end-use parts that we always imagine will bring about. So let's go into a little bit details here. Given the high customizable nature of additive manufacturing, exactly like the shoe sole that Alena referred to, it is no surprise that with the complexity of details, structures, or lattices, post-processing technologies also require fine-tuning to get that high-quality parts in the end. Maybe Alex, what's your take on this?
Yeah, sure. Thanks, Krish. So I think it's important to think about AM as being this incredible tool for having really detailed, geometrically complex parts where you can have particularly complex internal structures, channels, that kind of thing. But it presents an enormous challenge on the surface finish and on the post-processing. So for starters, it's almost an intrinsic part of AM is that there's a rough surface finish, or at least a rougher surface finish than what we're used to in the engineered world, and what we would like to see in the engineered world. And yet you have these amazing structures, and then you're trying to pair them then with post-processing technologies, because the surface finish may not be where you want it to be, and that can be very problematic. A lot of post-processing technologies are line of sight only, so that's machining is a classic example of a line of sight technology that's used for post-processing and is very, very effective. But the issue with that is that we're creating structures that aren't accessible with line of sight. So I've got a little part here, and I'll just hold it up for everyone to see. So you can see in here, there's a kangaroo on it. It's Australian. It's like a souvenir giveaway. So you can kind of see that there's an internal little thing in here, and could you imagine trying to get that polished? It's just basically nigh on impossible. You can't do it. And if you wanted to say, oh, well, we've got some gaps in between, we can kind of access it maybe with, I don't know, shot peening or something like that, you're going to probably damage the little fine structures that you've got there. So we almost have this we do have a real conundrum in additive manufacturing, which is we're constrained in our geometry often by our post-processing technologies. I think that there are ways around this though, and I think we like to throw everything back on the designers all the time, right? So we say, well, you can just design for that, design around it, and that's true. So, designers for AM, and this is where design for AM becomes so important, because you do design for things like knowing where, your upskin and your downskin are going to be. For example, so one has got a higher surface roughness than the other one. Also knowing how to minimize the support structures, because putting support structures, just automatically you're creating a rough surface right there that you're going to need to post-process. And then also creating your part such that you are able to access the parts of the part that you need to have post-processed, or need to be able to access with a line of sight type of technology. So we can use our design, I guess, smartly for post-processing, and I don't think enough attention has been paid to that so far. And I think that in so many instances, I mean, the industry in general is starting to wake up to this now, and is starting to realize how important post-processing and getting the right requirements for your surface finish are, especially, like I said, in the engineered world, but I mean also in consumer goods, because consumers can be very picky about how their things look, understandably. I know at RMIT, we have a whole research area literally just in cleaning lattices. So we have a lot of really great and amazing lattice structures that we're creating, but we have a whole new conundrum around then how do we ensure that we're processing those in the right way. And in many ways, it does lead to a redesign. So I've got this is an example of it's actually a dog jawbone here. But you can see there's a really complex lattice structure through here, and it goes through the whole center part of the implant. These types of personalized implants are great, but when you've got such a fine, detailed, how can you even, internal structure, how can you even ensure that you're removing all the powder? And then if you say go to heat treat, you're baking in loose powder. That's not what you want for a personalized implant or an implant in general. So, and then the other thing as well, I guess, is even when you've got your post-processing sorted, if you are doing things like personalized implants or personalized products, or even just custom type products, your post-processing changes every single time. So, it's not just your build file that changes every single time. It's also the post-processing steps that happen after that to ensure that you're doing it correctly. So, yeah, thank you.
Okay, thank you, Alex. So the next question, I think maybe a little bit touchy subject. Jenny, maybe you could pitch in here. So which ones do you see as the most used or adopted surface finish technologies in the market currently? I'm expecting a conflict, but please free open.
Yeah, no, I think I mostly can talk about the metal surface finishing processes that are available in the market. And I echo everything that Alex has said, because it's so important that the design engineers understand post-processing and surface finishing, because a lot of the methods that we have available in the industry are, they remove metal, right? And so we have to really allow for extra material on those designs in order for the surface finishing to get to your specifications in terms of geometry and as well as dimensions. So I think that's one thing that's very, very important. And like Alex was saying, like typically, and especially metal parts, they look like this, so they're very rough, right? And like we can be very creative in our geometries, and all of the methods that are available right now, all of them have pros and cons. And so I can tell you at least 5 methods that are available in the industry. One of them is abrasive finishing or abrasive honing. And really what this is mechanical action with a abrasive media, and it erodes the surface of the metal and it starts planarizing, right? So that's one of the techniques available. Another one, like Alex mentioned, is machining. And machining so far, gives you the best mechanical performance because it removes a lot of metal. And usually what it does is it attacks the surface defects as well as the near surface defects, or those defects that are just structures underneath the surface that we really can't see without microscopes or X-ray CT scanning, and those are really detrimental to mechanical performance. But again, like Alex said, machining is very limited in terms of geometry, right? So we have to find something else. Another possibility is electro polishing, and electro polishing is great for fine details. It uses electrodes and acidic solutions mostly to slowly dissolve material or metals from the surface, and it does a great job at producing aesthetically pleasing surfaces, but it also has a few limitations. Another one that we have, it's chemical polishing, and this is based 100% on chemical formulations. And what it does is that it dissolves the metal from the surface. So it's very good at removing partially melted powder, partially sintered powder. And it's also really great for those internal channels that we can access with machining, for example. The limitation so far is that it can't always get to very planar surfaces. So then sometimes they don't look as pretty as a machine surface or as an electropolished surface. And then another more revolutionary technique, maybe it's called chemical mechanical polishing, which actually combines the techniques from abrasive finishing, where you use mechanical action, but this time you can choose your media. It could be abrasive or it could be non-abrasive. And then you use chemical formulations to activate the surface of the metal, and then you both dissolve metal and planarize at the same time. And so this sometimes, because you really develop a formulation for every specific alloy that you have, you can accelerate the process, and you can also really reach all of those, or the majority of those near surface defects, the ones that you cannot see usually when you see a printed part. But again, you know, I think you really need to think about what is your need, what is the function that you're looking for, and all of these methods, no one is perfect. And so it really is going to depend on the applications and the needs that the customer has. But very, very, very important for design engineers to understand these processes so that they can help mitigate those issues. You know, if we can go away from surface finishing at some point because the designers, you know, sort of took us out of the supply chain, it would be great, because that means that additive manufacturing parts would be truly ready to use from the printer. But we're not there yet.
Yeah. Thank you, Jenny. When we start imagining the bigger scope of post-processing across technologies, maybe a question to you, Stephanie, since you're also on the customer-facing end. What do you see as a gap in the industry, or for customers in general? Is it tools, automation, adoption challenges?
In my opinion, I see the biggest gap being automation and possibly adoption challenges as well. So a lot of my customers on the post-processing side are still using very traditional manufacturing methods to post-process their additive parts, in particular surface finishing, their bonding, their sanding, painting, that sort of thing. So, you know, my job is to convince them to automate this process and teach them about the benefits of a fully automated surface finishing solution. You know, when you move to automation, you're going to eliminate a lot of the bottlenecking that these companies are experiencing. You know, they may have a tray full of parts they're waiting to post-process and simply just don't have the time to do it. They can put it into one of our solutions and, you know, have it done in a matter of hours. It's also going to eliminate the need for their employees to actually hand finish these parts, and they can be spending their time doing more productive things. And, you know, ultimately it's going to decrease their labor costs as well. So just showing them the benefits and how moving to automation is going to streamline their workflow is what I really enjoy about my position and my job. So a lot of education there.
Yeah, thanks, Stephanie. I believe we have touched base a little bit on the key bottlenecks in post-processing methods or technologies. To take a little bit deep dive into the topic we are discussing today, Alena, would you mind sharing your view on the key requirements for a surface finishing operation from your experience?
Sure, Chris. It's a very good question. Well, I think here it's especially important that we do not limit ourselves too much by post-processing, because freedom of design is one of the big achievements of 3D printing, and we should not limit this one by post-processing or surface processing. So therefore, I think that a geometry independent, geometry preserving, reproducible and scalable process is crucial for any surface finishing operation. And for sure, for me as a chemist, also things such as chemical and process safety play an important role. And this also brings me to another important point, because whenever chemistry is involved, and especially if you think about polymers, important for metals, but for polymers, you should always take into account that you will not alter the chemical structure of the polymer by post-processing, because this maybe would destroy your part. And if I have a bigger view, for example, for us at DyeMansion, we are not offering only one post-processing step, but different ones. And here we always have to consider that these individual steps can also be easily combined and that they do not influence each other in a negative way. So I would say these are basically the requirements which guide us in every new process development here at DyeMansion. So we usually challenge ourselves and ask, do we really meet our requirements in terms of sustainability, quality, non-destruction, and so on? And only if we can say a clear yes here, it's for us a go to really focus on a new development. But for sure, it's more than just the process. You should also think about the actual operation in the end. And there you should always take things into account, like an easy usage, traceability, and a smooth integration into production lines. So, and to ensure this, and it also goes in this automation thing, we at DyeMansion decided not to have just one individual process, but we try to have a reliable and well-coordinated post-processing chain with our print-to-product workflow.
Yeah, I think you made a great point that the entire process of printing, it's complete with a validated workflow that everybody knows, okay, it's not just one solution that fits all, but a rather customized workflow for each printer, material, and then how you clean or make the finish better. Now for more functional parts production or end-use parts, how well does the current surface finish methods or post-processing methods work? Alex, maybe you could share your view on this.
Yeah, sure. So, Krish, were you interested in like part performance? Is that what you were thinking of?
Yeah, exactly. So
Yeah.
how does the surface finish contributes in the part performance or quality of parts for functional or end-use parts?
Yeah, great. Yeah, so I think one thing that's really interesting, and it's been well known, it's so well documented and studied. Surface finish has a direct correlation with fatigue strength, and the reason that is I mean, there's other things that lead to, I guess, loss of fatigue strength, but surface finish and fatigue strength are kind of almost linearly linked. So the reason why is if you look at a metal AM part right up close, and we're going to take a profile, you've essentially got like little valleys and hills, essentially, basically it goes kind of like that. And in a really beautifully sort of micro machined part, you're not going to have those valleys and hills. If you've got a really demanding application, which say is like, and I mentioned fatigue, is a high cyclic load. There's a lot of fatigue stresses. What happens is those stresses tend to, they concentrate around the surface of the part. That's the nature of them. And so if the surface of your part has irregularities in them, what that means is you get areas or locations of high stress across the surface of that part. It's not evenly distributed, and that leads to stress concentration sites, and that is where a fatigue crack, which is essentially the start of your failure, will start to grow. It's a crack initiation site in these irregularity sites. So if you go through and really, I think, and I'm happy for any of the panel to jump in here, but the only post-processing surface finishing technology that really eliminates that is machining. Because with machining, you can come through and you can completely take off every single, you can go below the valley and take off all of those hills and everything above that. And then you do end up with a very smooth surface. And then and with the smooth surface, like I said, you get the stress evenly distributing around the part, and you tend to get much better performance. Whereas, like I said, if you have these valleys and hills, you'll get stress concentration, and you definitely get premature failure very, very quickly. And the other thing as well is corrosion. So if you've got a part in an acidic environment, marine environment, say industrial with sort of sour water or something, it can be very susceptible to corrosion. Corrosion is a nightmare. It's every metallurgist's sort of passionate hate, but also passionate area of study for many. And corrosion gets in, and it will degrade a part, and catastrophic failures happen from corrosion. So, and the way that corrosion works is that it loves to just accumulate in those little valleys. Basically, it's almost like tooth decay. So the better your surface finish is, the better your mechanical performance of your part will be, and the more it's going to behave like we expect parts to behave, because we are used to these conventionally processed parts, and we are used to expecting a certain amount of performance from these parts made traditionally. And if we can't get them additively, that becomes a real issue. So yeah, that's my bit. I'd be interested to hear what the rest of the panel has to say, though. Maybe Jenny has something to add. Yeah.
Yeah, I think absolutely agree with you, Alex. And when we look again at this part, you can almost see like the peaks and valleys, because AM is so rough. But then when we see a process part, maybe we start seeing it shine, and the light shines on it. You can see, on the other side, like it's not perfect everywhere. Like we're not going to sell you the stars. We're going to be honest with you. Like Alex was talking earlier about down skin and up skin surfaces. So sometimes you're going to have a difference. I don't know if you see inside over here, it looks a little different, right? But like Alex said, the majority or the surface finishing method that gives you the best mechanical performance is machining. But it's limited, right? So sometimes what we do at REM is that we use combination of processes that can get us there, especially for very high demanding applications. So I can show you, for example, we do some work with GR Cup, and I don't know if you can see it. This is like it doesn't have a lot of surface irregularities, but you can see this versus a finished surface. Now you have reflection of the light and things like that. And the reason why I bring it up is because GR Cup is a very specialized alloy for very high demanding applications, for very high cyclic loads, corrosion resistance. They use it for fuel nozzles and combustion chambers and things like that in aerospace. And in these applications, we're gonna withstand very high temperatures, very high cycle loads, and very prone to corrosion as well. So I think what's also important, besides just what we see on the surface, like I mentioned before, is the defects that are underneath the surface. So sometimes we get porosity from metal that wasn't completely fusioned during the printing process. Sometimes we can get keyholing effects. We can get lack of fusion between layers, and all of those, like Alex was saying, would also be fatigue crack initiation sites. And so it diminishes the properties that the part can have. So right now there aren't any processes that get to the same performance level as machining, but we're getting there, and we're getting there with combination of processes. Sometimes we use just maybe a chemical polishing formulation to get to those internal channels that machining is not going to be able to achieve. And then we use chemical mechanical polishing. For other areas that are easily accessible, and for some other areas they use machining because they cannot take the risk. And so I think right now, because designs are evolving, because applications are evolving, then also the surface finishing methods are evolving, but we're getting closer to that desired mechanical performance and material performance.
Basically, we just want a fluid that we can run through a part that acts like a machining center.
Maybe someday it will be. Yeah, thank you, Jenny and Alex. Among the many surface finish methods, so if we start investigating surface priming, adhesive bonding, or painting requirements, a manual component is required to manage all these functions. And that's kind of a sideway track of AM that nobody wants to look at. But Stephanie, do you see this evolve for post-processing to be more automated? And if yes, how far are we seeing the scope of the evolution of additive manufacturing?
Oh, yeah, absolutely. I definitely see post-processing moving towards automation. I mean, that's what personally I do. So my company, PostProcess Technologies, has combined hardware, software, and additive-specific chemistry and media to create a fully automated surface finishing solution, as well as support removal and resin removal. This process allows for repeatability and consistency with the additive parts for both polymers and metals. And then it also allows for a virtually hands-free workflow. So I'm definitely seeing the trend going more towards automation.
That's something we are all looking forward to, because I think that will really steer up the time and money that we are trying to save on the end workflow of post-processing.
Absolutely.
Thank you, Stephanie. Steering back to more detailed guidelines. So, Alena, what are the general parameters tested for evaluating the quality of a particular surface finish?
Well, I think today post-processing is clearly on the aesthetic and haptic side. So measurements like, for example, surface roughness, color shade, and gloss are the important parameters today. To really say if the part has a good or a bad quality after post-processing. But for sure, this should not be a one-shot success. I mean, now we are all thinking about industrialized 3D printing with post-processing. So it's important to meet these parameters permanently and in a reproducible way. And in addition, for sure, there are also other requirements like biocompatibility, color fastness, and mechanics of the components. And these should be for sure guaranteed during the finishing process and also during long-term use. I mean, you said it already, I think the UV stability, for example, for polymers is a big issue. And it's even a bigger issue, for example, for the dye parts, because usually dyes are not the most UV stable things you can have. So there it's important to also measure these parameters. So for example, UV stability or light and heat resistance are important for automotive interior applications. And in the end, it's like the parameters to be tested usually also depend on the final application. So each application has its own requirements, and we at DyeMansion, we try to serve our customers with as many certificates as possible to give them a good overview to finally choose the right solution for their application. But for sure, with new applications, also new needs for parameters to be tested will show up. So it's an ongoing process. We have to get more and more certificates everywhere to really serve all these applications in the end. But I think these are the most important ones, and especially the surface roughness is something which unifies all of us here. We have metal parts and polymer parts, but for all of them, at one point, everyone is talking about surface roughness. So this is something which brings us together here today, I think.
Great. Now let's take a peek into the main stakeholder, customer view. How does one choose the technology most applicable to the process based on the desired characteristic of the final part? So could you please share your experience on this, maybe based on a technology as a reference or a customer that you have worked with? maybe this is kind of open to the whole panel to share a little bit of your experience on this.
Yeah, maybe I can start and then the rest of the panel can follow. I would say that it will really, really depend on the final application for the part. And so if really what for metals, if you're just looking for a part that looks very nice and shiny, but it doesn't really have many applications, maybe in the biomedical field or in aerospace, then perhaps you can do abrasive finishing or electro polishing, where the parts look really great with very little metal removal. Like, remember, a lot of these methods are subtractive, so you're going to take metal away from the surface of your part. But if you're looking for something that is high performance application, then really you have to think about the method that you're using. Like, again, if fatigue life is important for you, then you probably want a method that removes the surface defects, like when we talk about surface roughness, and it also removes the near surface or those defects that are underneath the surface. And I can give you an example. We work with NASA, for example. A lot of the work that we've done and a lot of the technologies that we have developed come from a collaborative work with NASA. And we did, for example, we developed a surface finishing solution for Inconel 718. So these are not very fancy, but you can see this is the non-process, this is the process one. And Inconel 718, it's a very high performance alloy. It's very hard to get it to react, which is the reason why they use it in aerospace application for chambers and for fuel nozzles, right? And so what we've done is we've developed a chemistry that activates the 718, the Inconel 718, and then it starts removing metal, right? And what we have found in the work that we've done is that we have to remove anything between 200 microns to sometimes 500 microns from the surface of the metal to get rid of all of those defects that are underneath the surface. And NASA knows this very well, and they overbuild their parts, expecting us to remove that amount of metal to get the performance that they want. And so when I tell you that you really need to think about your application, I mean it, because sometimes your process can be done really easily, very fast, in a couple of hours with abrasive finishing, or it can take a few more hours or sometimes a couple of days when you do maybe chemical mechanical polishing. And so one of the examples I can give you, though, in this NASA project is the work that they're doing to go for the Artemis mission to get to the moon again in 2021. I can't remember exactly the date, but we want to get back to the moon, right? And a lot of the work that the nozzles and the rockets are being printed through additive manufacturing. And so one of the nozzles that we processed at REM has been tested by NASA, and it has been hot fire tested 23 times, and it was successful. Right? And so it really depends on your application. But like Alex said before, also the cost model that you want to use for your process.
Thank you, Jenny.
Yeah, I've got a really interesting anecdote to share, which was a real learning experience for me. So a number of years ago, I was working with a bike company, and they 3D print their bike lugs and use carbon fiber tubing to make completely customized bikes. They're really cool, and they're beautiful looking things. And they were 3 engineers that had been made redundant from the auto industry and were passionate about bikes. And anyway, they were looking at AM technologies, and at the time where I was working, we had a laser powder bed printer, and we also had an RCAM, an EBM, electron beam printer. So many of you would be aware that the EBM machine, or at least ours, because it was like an A1, it was one of the earlier generations, had produced parts with a rougher surface finish. And the laser powder bed system produced parts with a much nicer surface finish. It uses a finer powder. The layers are thinner. And the parts that we would get off the EBM, so it's built at an elevated temperature, and so generally speaking, the pad properties you get are superior to a laser powder bed without any heat treatment process. So the mechanical properties are better off the EBM system, and we did an initial prototype on the EBM system, and they looked at it and they were like, this surface finish is terrible. We cannot possibly use this for our consumer application, where, you know, it's not like they're covering those lugs in any way. Lugs are actually a feature of the bike and of the product. And so then we did some prototyping on the laser system. And they looked at it and they were like, okay, you know, we think we can work with this. And they've gone on to do a whole lot of other different types of treatments for those laser made parts, and they're now fully invested in laser. And one of them is painting. Some of it is just light polishing. Some of it is actually just raw parts, because some consumers quite like that look. But the point is that, you know, the EBM would have given them cheaper parts, actually, because, you know, when we went through the cost model, we worked out it was going to be cheaper. They would have been superior in strength, but it was not going to meet the customer expectations for what the part should look like, and it wasn't going to give them enough flexibility to do different types of surface finishing. So, you know, painting an EBM part wouldn't have really been an option. This is, I mean, I don't want to slam EBM because I love it, but you know, this was back in the day when you would get much finishes. So it was very instructional for me, which was, you know, as an engineer, you kind of always think it's about part performance, mechanical properties and all of that, but actually at the end of the day for them, the biggest deciding factor was, what does our customer like the look of?
Thank you, Alex. Yeah, just one of our experiences is on the cleaner. So with the photopolymer parts, and one of the material that we have is an FST material, flame retardant, and the cleaning process, the entire workflow has a cleaning process for resin removal, which primarily focuses, as you know, that IPA is one of the top cleaner that many of the companies use. And when you use it on a flame retardant material, you cannot really clean it very well because it's contradicting as to the properties what it is intended for. And then the requirement came up that we needed to create a non-flammable cleaning solution. And I think to go back to what everybody in the panel said, that it in the end, it always relates to the application as to what we need in terms of processes. But really great view. If there are no other comments, then we could go to Q&A. All good?
Hey, ladies.
Okay.
I think we're over. So
yeah, Amy's here.
I think we're over. I think we had until the hour. And so maybe we'll just take one question, but then we need to let people go back to the main stage and have a break before the keynote. So we'll take one question from the Q&A.
We have one question. So on the top voted, what are your thoughts on improving surface finish through the additive process rather than through post-processing?
Well, I can say something here maybe. So I think one big advantage of post-processing is also that you can achieve a big diversity. So for example, for our technologies, we have different smoothing technologies, a mechanical and a vapor smoothing technology, so you can achieve different surface roughnesses, and we have like millions of colors which we could dye. And if you want to do it in the printing process, you're always limited to one surface and one color. For sure, you could also do it in the printing process, but then you lose a lot of diversity. And in addition, I think if you improve the surface quality during printing, you will end up with a very, very slow printing process. At least what we have right now. Maybe in 5 to 10 years, there are so great printing processes out there that everyone is saying, yeah, post-processing for better surface quality is not necessary anymore. But right now, I think time of printing is one big issue which pays, or which tells us that post-processing is a good way to go, and then also the diversity.
Yeah, thank you, Alena. And to all participants, please reach out to the team here to answer your questions. And we really appreciate the detailed questions you have put in Q&A. But unfortunately, we are running out of time. And I would like to thank Stephanie, Alex, Jenny, Alena for joining us today. And to cover for Amy, we will definitely make a recorded version available for all those who weren't able to attend or just want to go back and review. And I would also like to thank our track leader, Amy, for pulling all of this to a wonderful conference. And we are happy to be part of this initiative and look forward to future exchanges. Thanks again, everyone.
Thank you.
Thank
Thanks,
you.
Krish.
Thanks so much,
Thanks for
Krish.
having me. Bye.
Thank you.
Bye.